Welcome, and it's a new problem solving session. We are taking some problems of thermodynamics, and we will be using first law of thermodynamics, the ideal gas equation, and related things. In this problem, we have a monoatomic ideal gas passes from state 1 to state 2. I think you can see this process here, state 1 to state 2 in one case along the curve 1A2. The curve A is from A1 to 2, which is a section of the parabola, simply written as T equals alpha V square. V is the volume here. And in the other case, along two straight segments, 1 to 3, which is a isocore. You can see volume is constant here, and 3 to 2, and it's a process. We will soon going to determine what amount of heat should the gas receive during the transition 1 to 3 to 2. If 2200 joule of heat were supplied to this gas during the transition from 1 to 2 through A, and temperature T1 is given, that is 250 Kelvin, and T2 is given 360 Kelvin. So that's a process here, and I'm going to analyze this problem on the basis of ideal gas equation first, and the equation is simply PV equals nRT. N is the number of moles of gases which is not provided. R is the universal gas constant, and the equation with which this needs to be used is given as T equals alpha V square. So if you wish, you can write here T equals PV upon NR, and you can further analyze it as P equals alpha by NR, that is a constant, multiplied by V. NR alpha V, sorry, I wrote down here P is equal to NR alpha V. Yeah, this is the correct equation now. So if we try to depict this whole TV diagram on PV plane, that is our strategy, to draw this TV diagram on PV plane. So that we can solve this problem easily, and I'm going to draw a PV diagram for this TV process, and I know this process T equals alpha V square. It's basically, on PV diagram it looks like this: P directly proportional to V, Y equals mx. So this is 1 to 2. This was the equation for 1 to 2 via A path. So I would like to draw a PV diagram for this, like passing through the origin, and this PV diagram is going to be like this, a straight line passing through the origin. And next, I would like to draw the process 1 to 3, which is B is equal to constant, so it's simply this, but I don't know how much length I should provide, so I would like to see this picture. And this is T directly 3 to 2 process, and this is like T directly proportional to B. That means combining it with PV equals nRT. I can see here T can be written as P upon nRB, and T is directly proportional to B. So P must be constant here. This is something like Y equals mx. So that means this 3 to 2 process is isobaric process. Pressure is constant here. So now I can draw the whole picture on PV diagram like this. 1 to 3 process is this, and yeah, and P is constant here. So I can give a proper symbol, so that is, this is 1 to 2 via A, and this is 1 to 3, and this is 3 to 2 process, and this is a PV diagram. So the value of pressure here, I would like to write it P1, and here as P2, and now what? So I draw that TV diagram on PV. Now what? Now I can see the work done in all the process. 1 to 2 process, the work done is this area, and since volume is increasing, so work done will be positive. For 3 to 2, I can also find the area beneath this 3 to 2 diagram, and 1 to 3, the work done is 0. So I'm going to apply now the first law of thermodynamics, and that is simply amount of heat provided equal to increase in potential energy. And you can see from here, this is always the increase in potential energy. T is increasing, and potential energy is a state function depending on temperature. So potential increase in potential energy plus work done by the system, which is positive. You can see here work done by the system. And now I would like to first write for the process 1 via A to 2, 1 to 2 process. I would like to write things like this. Change in potential energy, that is U2 minus U1 plus this is work done for the process 1 to 2, and this is the amount of heat supplied in case of 1 to A to 2. These things are positive, so positive things will be added and we will get the heat supplied. And for change in internal energy, we know the definition. Delta U is written as NCV, specific heat, molar specific heat capacity, delta T, that is that ultimately becomes Cv becomes R by gamma minus 1. Gamma is adiabatic constant. For monoatomic gases, the value of gamma is 5 upon 3, and so gamma minus 1 is 5 by 3 minus 1, that is 2 upon 3. So in this case, this delta U will become simply 3 by 2 nr delta T. And I'm simply looking to apply the whole process, whole first law of thermodynamics through the process 1 to A to 2, and that I'm going to apply it for this path it is going to be 3 by 2 nr T2 minus T1. This is the change in temperature here, plus this is the change in internal energy plus work done. And work done, I would like to write the area of this diagram, area covered by PV diagram with V axis, and you know this is trapezium, so I'm going to write down its area as half sum of parallel sides, that is P1 plus P2, divided by change in volume, and this volume here is V1 and here is V2. If V1 and V2 are also not given, but T1 and T2 are given, and we will find the way to replace it. But right now I'm going to write down this as, oh sorry, I wrote it here, I should have written here. This is half P1 plus P2, sum of parallel sides, multiplied by V2 minus V1, area of trapezium. That is the work done by the system. And for one thing, we know this process 1 to 2 process on this diagram, on this PV diagram, is simply like P is directly proportional to V. That means P by V, that means P by V is a constant, and you can write here, that means you can write here P1 by V1 equal to P2 by V2, and that means you can write here, you can get here P1 V2 minus P1 V2 equal to P2 V1. You can get something like that. P2 V1 P1 V2 is equal to P2 V1, and try to carefully multiply this, the right hand side of this equation, so that you can write 3 by 2 nr T2 minus T1 is known, so I'm not going to make any changes here, plus half, and simply multiply this. You will get P1 V2 minus P1 V1 plus P2 V2 minus P2 V1, and this thing you will get equal to 0 because P1 V2 is equal to P2 V1. So the result you will get is 3 by 2 nr T2 minus T1 plus half P2 V2 minus P1 V1. This is sort of energy here, and P2 V2 minus P1 V1 is what? You can use, you need to write down in terms of temperature, and you know from the ideal gas law PV is equal to nRT, so you must use it, and you can write here P1 V1 equal to nRT1 and P2 V2 is equal to nRT2, and this is the game we play in first law of thermodynamics based problem. And this is, now we have 3 by 2 nr T2 minus T1 equal plus I missed something. No, I didn't miss anything. So plus half nr T2 minus T1. This P2 V2, I place P2 V2 in place of P2 V2 nRT2 and P1 in place of P1 V1 as nRT1. So I got the results like this, and that means we can solve them together, and 3 by 2 plus half is 2, so I can write the final result as for the process 1 to 2 I can write it 2 nr T2 minus T1 is the heat supplied in this process, and its value was given. It was equal to 200,000 joule perhaps in the problem itself. Yeah, if 22,000 of joule during the process, 22, it was not 200 joule, but it was 2200 joule. So we have something, we can find NR from here, but one thing is still left to be calculated, and that is the heat through the process 1 2 3 to 2, in which 1 2 3 to 3 the work done was equal to 0. Work done was equal to 0, so potential, so 1 2 3 to 2 I'm going to apply for 1, so that I can write change in this is asked in the problem, so I can write change in internal energy is a state function, so it can be simply written as U2 minus U1, and the work done happened only during the process 3 to 2, so we need to find that out, and this thing is to be calculated in the problem. And U2 minus U1 I earlier calculated as 3 by 2 NR T2 minus T1, and I'm going to simply write down it. And 3 to 2 process was, I think an isobaric process, 3 to 2. So its work done will be simply, and here the pressure is P2. P2 multiplied by B2 minus B1. So I'm going to write down as this thing plus work done during 3 to 2 process as simply P2 multiplied by B2 minus B1. And so, however, this P2 can also be changed in form of NR, because the first result in terms of NR, so I would like to write P2 B2 equal to nRT2, and I'm going to put for P2 from here, and so Q1 2 3 2 2 is 3 by 2 NR T2 minus T1 plus P2 is nRT2 by B2, or I can skip one step, I can write it 1 minus B1 upon B2, and it's look like familiar. T1 and T2 are given, but what we are not given is B1 and B2, so I'm going to use the process 1 to 2, in which B1 B2 was also involved and T1 T2 was also involved in process in this process, and from this process one equation was given, and that was T equals alpha B square. So alpha is a constant here, that means T is directly proportional to B square. That means B square is directly proportional to T. That means B1 by B2 can be written as T under root T1 by T2. And I'm going to place it again so that the equation 1 2 3 to 2 will become, the question is getting longer, NR T2 minus T1 plus NR T2 1 minus under root T1 upon T2, and if I can place this T2 inside this bracket. I can also write it 3 by 2 nr T2 minus T1 equals nr T2 minus under root T1 T2. This thing can be written, and perhaps now we are ready to solve it. Sorry, this is plus, and now we are ready to solve this problem, because we simply need to put nr, the value of nr we got from here. nr is equal to 2200 joule divided by twice T2 minus T1, and I can write here nr is 2200 by 2200 by 2 T2 minus T1 by 2 T2 minus T1, and here is T2 minus T1 plus 22,000 by 2 T2 minus T1, T2 minus under root T1 T2, T1 T2 is given, and put all the values and you will get the result. I guess 2250 joule should be your answer. Thank you very much for watching.